この講演が英語でいたします。ちょっとタイトルはちょっと違うんですけど、今回はこのタイトルを使用する。Sorry, I would like to use English to present this talk. So the title is a little bit different. So today I would like to talk about reviewing the functional roles of the complex formation and dissociation of the tumor suppressor B53 proteins. And I'm from Tokyo Tech. So first of all, let's talk about the B53 and why I'm really interested in study these proteins. So this map indicates how the B53 interact and involve in the cellular cycle. So you can see that this is a really complicated map for interaction. And this is a shape of B53 monomer structure predicted by AlphaFold2. And actually, this protein is usually works together as the tetramer in cellular environments. And let's see the structure. So this protein includes the N-terminal domain and DNA binding domain, tetramerization domain, which help it to move together as the tetramer, and the C-terminal domains. And it has been found that the N-terminal and C-terminal is actually intrinsically disordered region, which is really flexible and which is really difficult to study in experiments. So let's talk about different things. I would like to talk about T. In some country, we call it CHA. And T is actually, most of the country in the world really enjoy tea, which is, I usually say it is the vitamin T. And we planted all over the world, especially Japan is really famous for matcha. And in tea, it consists of a lot of compound, and especially there's the polyphenol EGCG, which is really famous and thought to be, has been found indirectly that it can help us to prevent cancer. It also have inhibitory effects like aging or something. And recently, by experiment, it has been found that this compound is actually interact with the B53 in the N-terminal domain. And EGCG had a better affinity to N-terminal domain of these B53 proteins. And B53 proteins is actually related to a lot of processes like cell survival, cell death, and importantly, it is the tumor suppressor proteins. And EGCG also bound to make the N-terminal domain of B53 to be more subpopulous conformation. So the question is that what if the N-terminal domain B53 bound to its inhibitor, MDM2, which is suppressed it from functioning, and how EGCG behave, whether it can help us to prevent the cancer? That is the main question. So my motivation is that I would like to carry out the simulation of, I put a high concentration of EGCG and try to observe it, how it interacts with this complex, is MDM2 in complex with N-terminal domain of B53. And this structure has already been shown by experiment. So usually that to observe such kind of association and dissociation for really strong binding complex is really difficult. That's why we need to use more advanced simulation technique to observe that. So imagine that here you have the free energy landscape, and free energy landscape usually to represent how populated in nature of the conformation of the complex. And here, for example, here is the state A is more stable than state B, is more frequent observed than state B. And if you do the simulation such as the time scale is around nanosecond time scale, and however, it always fluctuates around the local minima at state A, but we would like to observe the transition from state A and state B, which is really difficult. But the rare events usually have the probabilities around 10 minus power minus 9. And if we do some really easy math by, if we divide 10 power minus 9 by 0.1 multiplied by 0.1 and do it, etc. Finally, we got this one. Inheriting in this idea, so we think about a divide and conquer. If we divided the free energy landscape into consecutively microstate, and we do the simulation and choose the outlier, and again, we do simulation again to observe the outlier, the transition between the microstate here. So finally, we can observe the transition from state A to state B reasonably. And we can do that in parallel and really friendly with supercomputer like Fugaku by parallel performance we call that parallel cascade selection molecular dynamics, or in briefly is the PAX-MD. So first, we trigger the parallel simulation with a really different predictor, and we choose consecutively outlier. Here in the case, we try to dissociate the N-terminal domain of B53 out of its MDM2 proteins, and slowly, we can observe the dissociation process here. So the nice thing from the PAX-MD is that we obtain a lot of transition between the microstate probability. And we think about the Markov state modeling, can it couple to the PAX-MD as well? So what is Markov state modeling? So imagine that you have you want to observe the stochastic process, and here is state A, B, C, D. And each time you perform some simulation, you observe the probability transition between those states, and you can make what we call is the cow matrix, like probability you observe from the simulation. But actually, if we think about the stochastic process, that transition matrix need to go to the time of infinitive. Is actually we be limited by the number of simulation that we observe. That's why we need to use maximum likelihood method to obtain the true transition matrix. And from transition matrix, we actually can calculate the stationary probability. And from that, we can calculate the free energy level and the kinetic rates, which is really useful for road design. So let's go back to a little bit. So from previous of my explanation, that I need to know the initial structure to trigger the simulation. However, if I don't know the complex structure, can I predict the structure in the complex and calculate the unit like by doing affinitive, K-on and K-off, which is really needed for road design. We think about more advanced technique we call AD PAX-MD, which A stands for association and D stands for dissociation. So we try to do a sampling exhaustive search for Bow conformation or intrinsically disordered proteins. So we try to perform the association and association consecutively. Like here, we sample the both sampling, and then we optimize both by just doing the classical molecular dynamic simulation, and then we construct the real energy landscape again by Markov state modeling. And eventually, the structure we found is actually really matched to the experiment. And so in practice, we have performed that with the N-terminal domain B53 in complex with MDM2. And some important interaction between N-terminal domain B53 with MDM2 is mostly the stacking between the aromatic residue from 2. And so you can see that it can optimize and perform formation of the helix on the surface of the MDM2 proteins here. Okay, so that is about the methods. So we would like to perform talks about the ECCG interact with B53 proteins. So we set up the system randomly put. Oh, randomly putting the EGCC molecules around MBM2 and B53 complex, and then we carry out the long simulation by just classical simulation, not the enhanced sampling simulation for this one. So accumulated is the 0.2 millisecond with the 1,000 trial here. So this is the illustrated simulation. So you can see that EGCC try to bound to the complex. And so we try to analyze the interaction between them. And we tentatively, we found that EGCC try to hijack the interaction. So here is the contact rate between EGCC to the MDM2 B53 complex. And this is MDM2 is occupied on the key residue recognition on the B53 on the surface of MDM2 here. And then the interesting thing is here, this is the interceptor mass between the MDM2 proteins and the B53 peptide here. And this previously we found, so here is the X-ray structure intercenter mass distance. And here, in the simulation, after we put EGCC and carry out, this is actually the peak after the EGCC bound. And here is another distance, a small portion of that distributed here. Is actually, this distance indicates that the distance between the MDM2 and B53 is going to the partially bound state, which is loosely bound between the two parts of the complex. So, however, we don't observe any completely dissociation between them. So, let's talk about the free energy landscape. So we want to identify what is the most populated structure through the free energy landscape again. So we construct the Markov state model, and then so this is the global minima. The free energy difference between the unbound EGCC to the complex is the minus 4.6 to the global minima in this RAM. And then we can see here that EGCC try to push its greens inside the interface, by bound interface between the MBM2 B53, and it hijack the key residue on that. So to be sure, it tried to hijack and it tried to mimic that. So we carry out the binding affinity in presence of EGCC of this complex by performing the dissociation proximity simulation. And after calculate that, this work with EGCC, the binding affinity is minus 6.8. But however, our previous study, comparing to the experiment, is the minus 8.9 kilocalorie per mole. So it's lower the free energy barrier. So it's encouraged the N-terminal domain of B53 to dissociate, and it help B53 to functioning. So this is the conclusion from this part is we find EGCC try to hijack and help B53 to be functioning and enjoy it. I would like to jump to the different topics is that we talked about the ASIC protein of HBV. This is HBV virus prevents the B53 interacting with DNA. So from experiment, so we found many evidence that the virus always try to affect the cellular pathway and interact with the B53 proteins. But however, the molecular mechanism is not really found recently. And among the virus, recently, ASIC protein of HBV is induced the degradation of B53. But from molecular mechanism, we don't know how it interacts with B53 and how it causes cancer. So we would like to carry out the study of interaction of this protein with B53. So this is the setup simulation. Here is on the right, this is the ASIC protein from HBV. And this is the B53. So we would like to perform the AD proximity we introduced previously to figure what is the molecular mechanism, how it can prevent B53 from interacting with DNA to cause cancer. So here is the movie that we illustrates how AD proximity works. So we try to find the bound conformation between the B53 and the E6 protein. You can see that it goes association and dissociation again and again within the cycle. And so after this one, we do relaxation and we try to figure out the interaction between the HBV E6 protein with the B53. So here is an interaction map. Here is the B53 residue index, and here is the E6 residue index. So you can see that the highest populated of the contact map is occupied in this region, and which is the WWOX interaction region on the B53. And this region is actually the DNA interacting region on the B53. So this is the summary of the AD proximity process. This is the final complex that we obtained in the most populated structure. So we try to compare it, whether it's true, how it interacts with the DNA. So here is the structure we obtained previously from our simulation of the B53 tetramer with the DNA. And here is the in the cyan color. And in magenta color is actually this study. We performed AD proximity and we merge, superimpose both structure on the interacting with DNA. You can see that this helix is actually occupy the DNA interacting region here. And if we rotate it 90 degrees, you see that the same region is interact with the one monomer on DNA, which means it prevents the whole complex to be tetramer to push into the DNA here. So we would like to have some concluding remark from here. Is the viral protein E6, it tends to occupy the DNA binding region and some main interacting of the B53 toward DNA. And in addition, the E6 protein also tend to interact with the region on B53, which are found to interact with WWOX, strongly related to breast cancer. So thank you.